Hello everybody, and a warm welcome to our virtual talk today. My name is Verena, and I'm a member of the Powtech Technofarm team, and together with Christine Montini, your host today. So first, I would like to inform you that we will record this virtual talk today and make it available online afterwards for you. And yes, as you will have noticed, your microphones are muted, but don't worry. So we have a short Q&A session after each talk. So please feel free to use the F&A button to submit your questions to our speakers. But yeah, now let's go into our topic today. First, many thanks to our partner, the VDMA, and in particular its competence associations for air handling technology and process plant and equipment for shaping our program today. And especially the thanks goes to Christine Montini and Natalie Wagner, and to our three speakers who will providing practical insights today into the process side of battery production, dry room design, extraction and filtration, particle risk management, and recycling. And yes, Powtech Technofarm will follow on from this in September and offering the community an international platform to discuss these topics live and develop solutions together. And yes, now I wish you exciting new ideas and fresh perspectives and an inspiring exchange of ideas. And yes, hand over now to Christine.
Yes, thank you, Verena, for the nice introduction. And I would like to introduce Dr. Stefan Jakschik to you. He is obtained his PhD in semiconductors at the Technical University in Dresden, and he is the CEO and CTO at ULT AG since 2023, and where he is acting as the head of research and development on process air cleaning and climatization. In addition, he is a board member at VDMA Battery Production since 2016 and the chair of Neo.net Association since 2018 and has over 15 years of experience in technology industrial leadership. Dr. Jakschik, we're looking forward to your insights on technical cleanliness.
Thank you very much for the introduction. I also share my screen. And hopefully everybody sees the slides now. Thank you everybody for joining this afternoon, and especially also to you, Benedict, for this presentation, which makes it easy for me to move on a specific topic from one of those you highlighted. So you mentioned especially that learning in a scaled up production and a big volume production is essential for innovations and for further development. So this talk focuses on air, on the environment in a battery production, and it also shows how this learning effects should be applied in there. So we identified 6 measures of a reliable production from our point of view, from environment and air. So first thing is the product design for manufacturability. Second is process design, then the environment where you do the process, the tool design, some inline metrology topics and material topics. And at the very end, I will also tell you what makes it the Magnificent 7. But let's walk through these topics first. Before we start, I'd like to explain what drives us at ULT in the market and in economy. First, we are focusing on employees' health. If the air is clean, everybody stays healthy. If not, you have the risk of losing work time, workforce. You have long-term effects on health and definitely also on motivation. And second, you also want to focus on a reliable machine operation. If there's too much dust and particles flying around, machines getting deteriorated, and you have very high maintenance costs, downtimes, and also rework to be done. And the third, and also in battery production, extremely important, is product quality. The product quality in many processes depends strongly on air and and particle-free production. I think such a watch production is very intuitive for every one of us, but this is true for many processes. And I'm sorry for showing you this very bold pictures here in the beginning with some German words on it. But these are examples of burnt down cars because of particles or moisture in the production processes. And this is what Benedict also mentioned in the beginning, that battery production seems to be always a bit too late if you recognize things in the battery, and this is also true for reliability. If there is a particle during the production process available, sooner or later this very particle could be the cause of a battery short, which leads to thermal runaway and failures like this. And I think this makes it so important to learn how to run a reliable production, also in terms of clean air and clean production processes. So this is a motivation for this kind of work we do in this market. And as promised, first I want to talk about product design. And I see there are many people in the listening today which have much more experience than me on product design, but I look on it on a way of particles. How do particles, which impact have particles in the product design? So these are the three major ways you can make a battery cell. You can make a pouch cell, a prismatic cell, or a cylindrical cell. And since the pouch cell has a lot of operational steps involved, the risk of particles is the highest in pouch cell production. But it's less critical because a pouch cell is not stiff and hard. It can kind of move a little bit, so particles don't necessarily short this cells down because it can modify its shape a little bit. The other tools, the prismatic and the cylindrical cell, they are very stiff. They cannot move. All the material is pressed in. So here particles are much more critical. The good news is, since the production is less complex than a pouch cell, it's also less particles available there. Especially for the cylindrical cell, which may have best process control probably on that kind of production. So what are the sources of particles in a production process of a battery cell? So if you walk through it from the very beginning, you start with dosing, and then you do the coating. Coating, drying, calendering, slitting, drying, you know all these production steps. And I showed you what kind of materials are exposed there and could deteriorate the cell. The coating, drying, slitting, and the other drying process, there are gases available, odors and vapors which could modify the cell. And slitting is in some cases done by laser. The laser produces very small particles. I have some pictures of these later on. Particles which need to be taken care of during the production. When moving on and separation, stacking, packing, filling, you also have the same kind of critical steps available. Separating is nowadays done by a knife or laser. Especially laser produces this very fine particles, and you have to be aware of moisture in these steps. As closer you come to electrolyte filling, as more important is moisture in the production process. So from our point of view, water or humidity is also a critical particle or a critical gas in the air which need to be removed for the battery production. So we have some examples. You see here a pouch cell, a prismatic cell, and where these cutting processes take place in this kind of production. And when we look on our filters, which run in this kind of productions for this slitting process, we see a lot of this dust in the filter. So that means there is indeed a lot of dust available, a lot of particles available, which need to be taken care of. If you have them on the filter, everything is nice. If you don't have them on the filter, something is weird in the production steps. So this laser process, which we just looked at, takes place like this. Very often you have scanner processes running over the electrode. And when we look to the particles, you see something like this, especially when you work with a short pulse laser. You have some balls, but mainly it's kind of a woven, as you see here, very kind of dendrite-like particles. For the ones of you who are aware of batteries, dendrites are very often lithium dendrites, but these are dendrite kind of looking particles from the laser slitting process, which could be on the electrode surface after this production process. Further on, when you put everything together in the pouch, you have a tap welding process. To my experience, this is the most underestimated process because very often it's done by ultrasonic welding or laser welding, and many people don't see the particles, and I very often hear from the market there are no particles on that step. This is not true. When we do a particle analysis here, we also see a lot of particles, especially you remove also particles from previous production steps and bring them to very critical positions in the stack or in the cell here. I want to walk you a little bit deeper into this kind of particles which can be exposed during laser processing, and this is a test we made in one of our labs. You have a laser production on an electrode surface, and we investigated lithium titanate and the LFP, which is nowadays the common electrode, and you see the kind of particles we see over there. A lot of balls, dendrite kind of particles. Most of them have the size of 100 nanometer or below. So barely visible, by eyes definitely not, and also by many sensors and vision techniques you would not recognize them. So a very good capturing of the particles is extremely important on that side. But before we come to the capturing, which is machine design, I want to talk about the environment where the production takes place at all. And this is the dry room. All these critical production steps, as I mentioned, close to electrolyte filling, are done in the dry room. And since there is no moisture available, many materials act in a different way. So you definitely have material degradation. Some degradation takes place because of chemical reactions are made possible since the protective layer, the protective moisture layer is missing. So materials wear faster than usual. And also the kind of friction and stress-induced degradation changes. So we also saw kind of a debris when moving materials over one each others, or just by aging effects of this kind of materials. A lot of investigations on that one, and also the bad news here is you have the bigger particles which you can see, but this kind of material degradation also produces small particles which are barely visible or detectable. So when selecting the material for a dry room, special attention needs to be taken on what kind of material you use in order to minimize these kind of effects here. So as promised, I like to come to the tool design. I mentioned already 2 or 3 times up to now that a lot of these particles have a very small size. And on the left side, you see on the X scale the diameter of the particles, and on the Y scale you see on the Y scale you see the particle size, and on the X scale you see how long does it take for a particle to saturate. And it takes very, very long for very small particles, for particles of 100 nanometer to come to the surface. Essentially, you have them always in the air. A particle of 100 nanometer will stay 14 days without any, or 30 days here, without any interruption before it comes down to the surface. But in a machine, you always have turbulences, so these small particles are always in the air. And so it is very important to suck them in a suction element as fast and as complete as possible. We made some visualization of this process shown on the right side in green, where we put certain light on in the air and a lot of particles in order to see how the particles are captured. But for the machine designers here in the round, I want to talk about 2 or 3 very important topics to be taken into account. The one is you have to make sure that you capture really everything or nearly everything. So in this picture, you see if you have 100% of the particles and you just capture 90%, you still have this more than 10% of particles in the air which could degrade the battery in future operation. And how to do this, how to make a proper capturing, that's shown on that slide. First thing is go as close as possible to the source of the particles. If you see on the left side, if you double the distance, capturing efficiency is getting worse, and you need 4 times of volume flow, which in the end is a lot of additional money or cost involved in it. So try to come as close as possible to the surface. And the second picture shows also try to use a flow in the machine. Think about where is the fresh air coming from, the clean air coming from. This clean air should be above your battery cell, and how you capture the particles, preferably behind the electrode material or the separator material, in order to avoid that any particle could saturate on this material. And the third picture just reminds every one of us that all of these process steps are dealt with conductive material and burnable materials. So you definitely have to make an ATEX secure installation. We know from some installations in the field where people took not enough care of this topic, of the ATEX topic, and got severe damage in machine and probably also employees. So we strongly recommend to put a lot of significant part of the engineering power in doing this ATEX evaluations during your process when you deal with air and particles. So after we did everything what we could do, after you have a proper clean room, a good tool design and a good suction, there's still the risk of having particles on the surface. So an inline metrology after these kind of steps is strongly recommended. So an early detection of these particles on your surface could reduce any scrap cost later on, or even reliability topics in the market. In addition, we also strongly recommend to make a detection of gases, because if a laser is operated on a typical LFP electrode, there is some risk that acids are produced like HF, especially if you work with a PTFE material involved there. This hydrofluoric acid could be produced. So we also in our installations always work with HF detectors and also HF filtration to make sure that no acid can deteriorate your battery cell or your equipment or your employees in the worst case. So that's about inline metrology. And finally, I'd like to show you a installation, which is definitely not the biggest one we made, which you need for all of this kind of particles produced during the battery cell manufacturing. So you see on the right side a cyclone, which takes out the biggest particles, and then comes the filtration unit. And we have a filtration unit modified in the way that it also gets rid of the acids, of the hydrofluoric acid, and in some cases chlorine acid. So after the filtration unit, most of the acid and particles is out of the game, and the 2 black bins on the left side are responsible for all the odors and additional gases in the production flow. So this is a typical industrial machining setup for that kind of processes when you want to make sure that you have a perfect filtration where you work on. So with that, I'd like to come to the end. I promised to talk about this 6 levers needed to be taken into account. The design for manufacturability. So think about when you think about your process, you also should not just think about the specs, but if possible also about how to minimize particle sources and how to design the product in a way that particles in the product don't play such a critical role. Then it comes to process design, always think about what kind of steps you need. Some produce more particles, other ones less. And third, very important in battery manufacturing is the environment. Clean and dry is a very simple answer there, clean and dry. I did not talk too much about how to improve the environment further, and this is the picture on the right side, which you see here. So to our understanding, the most effective way of getting a very good environment are mini environments, where you have a certain housing around your machine, your tool, and within that housing you supply the right amount of environment, cleanliness and humidity, but you also take care of all the particles which are produced during the production step. So this is something where ULT especially focuses on, and where we also have a lot of experience from the market. And you see here an example of an installation where we brought everything together, the mini environment, the dehumidification, and also all the filtration tools or necessities you have. The fourth thing is tool design. It's also always good to bring the designers of the machinery company in contact with the ones who make the mini environment and the filtration technique, because that could really save money, invest money, because you can work with less air volumes and so on, but also it also saves definitely operational cost. So we really went into depth with it, and with something like which you see on the right side, you can save operational cost by 70% compared to a standard ballroom design. For the production, and that's definitely in the ramp-up rate, we strongly recommend inline metrology. It could be reduced later on, but don't be too reluctant with inline metrology in the early phases. And it's also very important to think about what kind of material is processed. Well, all of these 6 levels are made to the magnificent 7 when you think about people. People are the major source of humidity in a ballroom design, and you keep them out when you work with mini environments. But also you need the people to look on all of these steps. Are they probably implemented in your production processes? Everything running well? A good service, a good maintenance is always a good lever for fast ramp-up phase and high yield production processes. So I would be very happy to stay in contact with you. I put in my LinkedIn QR code on the right side. Just scan it and connect with me. If some questions come up after this talk 1 or 2 days later, just write me on LinkedIn. I would be happy to discuss these with you over there. Thank you very much.
So thank you for exciting insights, and we shortly can start with our Q&A session. And I can see the first one. Your presentation was referring to wet electrode production process. Do you see any differentiation in requirements for the dry electrode production process, DBE?
So yeah, definitely I took in the wet production process. You have different coating and you have the drying process to be done afterwards. Many other steps are very comparable. So also when you do a dry production, you have the slitting to be taken into account, and certain humidity and particle topics starts earlier in the dry production process. So I would also already right after the calendaring take care for good suction and filtration if there are some residual particles left over there.
Okay, thank you. Then we have another question. Are there any limitations for usage of, for example, EPDM or NBR in a dry room environment?
For EPDM, I think that is something we would also use, definitely. For the other material, I have unfortunately no experience. I'm sorry. Very specific. If you write me later, probably on LinkedIn, we can look up in our database if we have some information on this.
That's a good solution. for this question. So we have another one. And why is production know-how specifically so critical in Europe?
So if you do production always on a very small scale, like a lab scale or a small scale, then a lot of these small failures, these very small failures which come by statistics, are not recognized. And the solutions you bring into the game could be systematically wrong on these. So if you ramp up, then this could become a pitfall, and late in a ramp getting recognized. This is one thing. The other thing is economy of scale. So economy of scale always lowers the capex and helps in fostering innovations in the game. So what we learn from other technologies, and the ones of you who run a high volume, high yield battery production know that probably as well, that it's a big step coming from a yield of 60 to a yield of 80 and to a yield of 95. And there's always innovations necessary to go these steps from one to the other. And when you do the learning, when you come in the learning phase, you also learn what kind of measures you need and what kind of measures are kind of over engineering. That's what make a high volume, high yield production usually getting cheaper, since you can easily work with statistical methods like Six Sigma and so on to reduce further cost there.
Okay, then we have one last question. And this, in which areas are mini environments most effectively applied?
Yeah, thank you for this question. So first of all, a mini environment needs a certain maturity of the process. So the machine which you have in the mini environment should run well, at least 40 to 50 minutes without human interaction in order to work it very well. Mini environments are especially helpful when you go to brownfield installations, which probably run at a dew point of -20 or -40, probably -40, and you start up with a new process like lithium sulfur or sodium or whatsoever, which needs higher dew points like a -60 or above. Then such a mini environment is a very simple, cheap solution to enable your brownfield installation to become capable for these new technologies. It's one thing. The other thing is, if you have a mature production process and you think about starting a new production line, then you really should take it into account. We made a calculation for a standard lithium cell process, 1 gigawatt. You could save 2 million of operational costs when you go to mini environments instead of a ballroom design.
Okay, thank you very much. And yes, we finished now your talk. Thank you, Stefan.
Thank you very much
for your insights. And now, Christina, we move on to our next speaker.
Yes, indeed. Our next speaker, thank you, Dr. Jakschik, for the insight, of course, and I'm reminded of my clean room technology times. I'd like to introduce Stefan Sander next. He studied process engineering and mineral processing at the Freiburg University of Mining and Technology, where he continued to do research on the comminution of metals in recycling processes and received his PhD in 2002. After 10 years in various research and development related positions in the paper industry, where he focused on paper making and paper coating technology, he joined Hosokawa Alpine Aktiengesellschaft in February 2012. He is currently the head of research and development of the powder and particle processing business unit, with a strong focus on size reduction and classification for all types of applications. Dr. Sander, please, the floor is yours, or the screen is yours. Thank you.
Well, thank you for the kind introduction, and thank you for the chance to having this talk today. I'll share my screen. So well, you should see. Well, good afternoon to everyone. I'm going to talk about the direct scrap recycling in lithium-ion battery manufacturing. This is maybe a topic that not every one of you will bring us into contact with. But before I start going into detail on the process itself, I would like to introduce our company for those of you who do not know us. Hosokawa Alpine is a very traditional company, more than 125 years old nowadays, and we work with approximately 800 employees here in Augsburg and up to 40 additional employees in Leingarten near Heilbronn. We have two business units. The bigger one, accountable of about 60% of the annual turnover, is powder and particle processing, and I'm heading the R&D department for this business unit. And the second business unit here is the film extrusion equipment. So in general, we are equipment manufacturer for all kind of applications. And we've been part of the Hosokawa Micron Group since 1987. And the Hosokawa Micron Group itself, so Hosokawa Micron is a very traditional company itself. There is still a Hosokawa family who owns most of the shares of the company. And as you can see, we have approximately 2,000 employees worldwide. Of course, headquarters in Osaka, Japan, but there's some sister companies of ours, and of course our daughter companies spread around the world with a focus in Europe, but also North and South America. We have several activities in the industry or industrial field around lithium-ion batteries, and if you see at this sketch, so we are active in manufacturing equipment for our customers who produce mainly raw materials or cathode active materials if it comes to the cathode side. For the anode side, we provide equipment for grinding and dedusting, but also shaping of graphite, fine grinding of silicon, for instance, and other anode materials. Of course, if it comes to ceramic separators, also the raw materials are manufactured using our mills and classifiers. But we are also active in the recycling field and also have solutions as a group for containment and all kind of equipment for the safe handling of the materials that are hazardous in some cases. What's quite important, I think, is if you are talking about production scale for lithium-ion batteries, that you need to have, I think, the ability to have a look at the complete chain during an scale up of a process. So we are able to support in the phase of R&D, but also if it comes to pilot scale, we have our own test centers, but we are also able to provide pilot scale machines. But we also do the design and also delivery of complete production plants. What brought us to dealing with the topic of direct recycling in lithium-ion battery manufacturing was the information we got that nowadays the well-optimized processes, if it comes to battery production, produces 7 to 8% of the coded electrodes as scraps during the different steps in the production, and a big portion of these scraps are separated, and you can collect them separately and also treat these scraps separately. And during a startup phase of such a gigafactory, up to 50% of the electrodes that are coated will end up in the scrap. So what is the situation nowadays is that these scraps are sent to the recycling plants for end-of-life recycling. So where used batteries are recycled, and they come into the big pile, a big mixture of all kinds of electrode chemistries, of a big the back mass that's produced there is a big mixture of anode and cathode material, and also all kinds of additives, but also impurities that come into the black mass during the recycling process. And we thought there might be better ways to do it. Another important issue here is that due to the regulations for the European battery industry, not only the recovery targets for end-of-life batteries will increase during the next years, but also the minimum amount of recyclate that has to be used in the production of new batteries will increase during the next years. And this is a pretty rapid increase. And so I think battery producers, battery manufacturers have to make up their mind how to deal with this. So that was the, let's say, initial motivation for us to deal with the topic of direct scrap recycling. We thought there might be a better way than bringing the production scraps to the plants for end-of-life battery recycling, and we are proposing a process like this. So during the electrode manufacturing, there's electrode scraps that can be handled separately. So you exactly know the chemistry of the coating. You know not only the chemistry of the cathode active materials, but you also know exactly what kinds of additives you use, binders, all kind of additives. And the problem is that most of these scraps are either on reels or coils, or on the other hand side, you have scrambled up fragments of these scraps. You cannot process these materials using, let's say, industrial techniques so good. So that's why you first of all have to convert this stream of scraps into a manageable bulk material. And then, of course, you need to gently delaminate the coating from the electrode foil. So these electrode foils are very thin metal foils. We think that mainly this would be applicable to cathode electrodes, since the value content is much higher here. But basically, that could also be used for anode materials. But you have to delaminate the coating from the foil, and then you need to separate the electrode foil. This will go to an external recycling, and the active coating material that is collected in the fines of this separation step here, in some cases has to be further processed, and we were thinking that it might be possible to bring this material directly back to the electrode manufacturing, and there's publications out there that indicate that this is really feasible. So there's if you do it right, there's no detrimental effects on the quality of the electrodes. That's the lab scale still, but I think I'll show that we are part of a joint project where we would really like to challenge this process and go to the next scale here. For these single process steps, we have different solutions at hand for this conversion into a manageable bulk material of these scraps that coming from the production. We could use cutting mills that are specially designed to have a low effect on the electrode foil itself, so low degree of impurities and so on. For the delamination, there's two different processes I will show you later on, one using an impact fine mill and the other using a fluidized bed, a post-jet mill that is operated in a non-conventional way. And then for the further processing of the material, we have classifying mills available, fluidized bed jet mills. That's basically the same type of equipment that's used for the production of the virgin materials. One process route I would like to show you is this one using the fine impact mill. So the material that comes here is first of all, as I said, transferred into a bulk material using the cutting mill. You see the material down here that's coming out of such a mill. It's fragments below 1 centimeter, and these fragments are then fed to the fine impact mill. These impact mills are used also in end-of-life recycling. We've delivered real big mills for these end-of-life recycling processes. But in this process, the process conditions are much gentler compared to the end-of-life recycling. So we get stressed material as a result, and here delamination of the material has taken place. In the next step, we have to separate the electrode foil that still carries some residual coating material, and the fines of this classification step, this is the active coating material. Of course, the binders, the additives are still present in this as a mixture. As you can see from the particle size distributions down here, this material is way too coarse to bring this back to the actual electrode manufacturing process. That's why if you would really like to go the direct way, you would have to process the material further. For instance, with a jet mill, fluidized bed jet mill, and you can see you can easily obtain the same particle size distributions you are used to with the virgin materials. These cutting mills we use, the Autoplex, they are, you can see the rotor here. They have a special rotor design that reduces dust formation and formation of impurities. And by changing the discharge grade here with different designs, you can adapt also the fragment size, and you can you can adapt your process to the needs of your product. But since this is something we've learned so far, every material, every scrap is a bit different, behaves a bit different, and needs some other process conditions in order to get a good yield with low impurities. Then in the next step, this delamination takes place with a fine impact mill. You can see the size that has been delivered to the end of life recycling processes. So here you have also the rotor and stator setup to adapt this process step to your needs, but also the process conditions in terms of the speed of the rotor, but also you could improve the results by cryogenic treatment of this of the scrap material if this is preferable. So afterwards, you come up with a mixture of the delaminated electrode foils and fragments and the fine material that is the active material or the coating material. And you need to separate these two fractions, and we use classifiers for this, mostly this deflector wheel classifier. So here you have a deflector wheel rotating with high speed, and you suck in an airstream or gas stream, you can suck the material through. And this air volume flow is set into rotation by the classifier wheel. And so you have two different forces acting on the particles. And for the finer particles, the circumferential speed or this the force acting to the outwards is lower than the drag force by the gas volume flow. So the fine particles are sucked through the classifier wheel, and the coarse particles are deflected by the wheel. So you have a separation between fine and coarse. And the fine material, that's actually the coating material that has to be recycled. And as I've shown you, you can further process this material for obtaining the needed particle size distribution here. And you can see the outside of a jet mill here, but it's quite common to protect these the inner surfaces of these mills with all kinds of ceramics in order to avoid contamination by metals coming from the mill itself by abrasion. We've also shown that there's a bit simpler process feasible by exchanging the combination of the fine impact mill and the classifier with a semi-batch operated fluidized bed jet mill. So you can see the first jet mill here, and of course, again, the fine material, the coating material is still too coarse to use it directly for the recycling material. That's why, of course, also here a subsequent treatment with a second step is necessary. Again, you can see the electrode fragments that come directly from the first jet mill have some residual coatings on top, but you have the separation during the delamination in this case, and we've seen that the yields are a bit better using this process, and also the tendency to form impurities is lower using this semi-batch mode jet mill here. You can see how this works. The material comes into the jet mill. In this case, it's not continuously fed, but you feed a material batch, and then you stress the materials using the jets that are usually used for the comminution of the material. And after during the process, the delaminated material will be discharged through the classifier. The electrode foils with the residual coating are held back inside the mill and sent back to the let's say stressing zone down here. And after the batch time, you can discharge the electrode fragments from the bottom. So this takes about 5 to 10 minutes, such a batch, and the feeding and also the discharge is done in below 1 minute. So you can adapt the cut point by the classifier wheel rotational speed, and that's why you can very well fine-tune this delamination process here. We've seen that the pretreatment with liquid nitrogen, so like shock freezing of the material, can improve the delamination, but it's not necessarily economically. We've also thought about an industrial scale process. This is how such a process could look like at the throughput of 1 ton per hour, which according to our rough calculations would be let's say the size for a gigafactory that's needed. Of course, this process could be much more compact than it's shown here, but then you wouldn't see anything. Of course, you do not need a filter for each of the processes, but in this case, we've chosen this design just to see the the concept. You feed the material here into the cutting mill. Then you have here the impact mill, fine impact mill. After that, the classifier here, where you separate the material, the fine material that goes into this filter and then can be fed to the jet mill afterwards for further processing. This has to be decided in any case if it's really necessary to have a jet mill here. Maybe let's say a more cost-effective classifier mill could also do the job. That has to be decided case by case. But I think you get the concept. So it's a substantial plant. And of course, this will not be placed inside the manufacturing area, so but should be very close by. And of course, the same issues have to be taken into account if you think about a plant execution here. Of course, in order to save space, you would have to need a much more compact layout of the plant, but that is, I think, also to be decided case by case. Of course, in some cases, most of the process can be run dust proof, so you do not have any dust formation outside the process itself, but during cleaning, during changes of the containers here, for instance, but also if you have to do maintenance and so on, you might need special solutions for safe handling and also operator protection. So we offer a wide range of containment solution like downflow booths, isolators, glove boxes, and so on, in accordance to the occupational exposure band that has to be taken into account. So dust has to be prevented in any way in such an installation. Of course, a high degree of automation, it was mentioned earlier today already, helps. So process control and automated sampling is also a thing to take care of here. Of course, ATEX is an issue that was mentioned before as well. So I think we have a wide experience in ATEX proof plant design from chemical industry, but also food and minerals industry. And of course, this is important in this respect too. And of course, by tuning the parameters of the equipment, you can adapt the process to the needs of your material. So to sum up, we've seen that the process must be optimized according to the properties of an electrode scrap. Each scrap behaves differently, needs different parameters in the process in order to obtain good results. both process routes I've shown can be adjusted by various process parameters to meet the requirements. And we have a test facility for first tests available, where we are also able to handle hazardous materials as NMC and other hazardous materials. And you see the material, the equipment we have available there, so we can also go through the complete process there. But the process will be challenged and further developed during a joint project we've just started beginning of this year, and it's called SCAREC. It's a funded project, and you see the project partners here. So together with VATA, Elite, Eura, and ACP, that's the industrial partners. And together with the IPAT in Braunschweig and Hochschule Aalen or University of Applied Science in Aalen, we are challenging this process and are going to further development to further develop this. Okay, this being said, I would like to thank you for your attention, and will be open for questions. And yes, we will be at the PowTech as you can see, in hall 7A, booth 530. Thank you.
Thank you, Stefan, for your talk. And I can see some questions for you. I think we start with the first one. Do you have experiences in both technologies, slurry and DBE production? You are focusing only on production scrape, not on recycle and reuse of batteries after end of life. That's a question.
Of course, this is our focus. We offer, as I said in the beginning, we offer the equipment for size reduction and classification, and of course the complete processes around these, let's say, core unit operations. We usually work together with customers that have the ability to test the materials afterwards. But we also have a partner on site where this little test installation is here, that is also able to make, let's say, small cells, and does also analysis for testing the materials. But we do not have own equipment or facilities for doing batteries and things like this.
Okay, thank you. Then we have a question about the recyclate rates. So is direct scrape recycling the answer to the battery directive and its targets for recycled contents?
It's not the sole answer, I'd say, but maybe it could be an aspect to that. Yes. I have to say, so far, it's not done on industrial scale. So at the moment, we are talking to several partners, and well, this is also the reason why we've taken part in this joint project to learn more on the, let's say, feasibility of using these materials directly. But if this should not be feasible, it must be a big advantage to use, let's say, well-defined material. Also for, let's say, longer loop recycling as well. But we think it could be one aspect of a, let's say, circular economy. Yeah.
Okay, thank you. Then we have another question. The process route shown featured a large number of cyclones and filters where explosive atmospheres are likely to develop. How is safe operation guaranteed, and what explosion protection measures are implemented?
Well, that really is an issue that has to be addressed. I mean, there are several measures usually in most of our applications. You always you will always have a source of ignition. So you always have like three options. You can try to have a protective system by not having an ignition, and that's if you have, let's say, rotors running with high speed, you can never say that you have no source of ignition. That's for sure. But then you could run this process, and in some cases this might also be necessary to protect the material itself from oxidation or other detrimental effects. It might be necessary to run under inert atmosphere. In this case, we could use recycling of the process gas, so that the demand for, let's say, inert gas reduces significantly, and you usually only 10% of the process gas has to be renewed, so the rest of this can be recycled. Or of course, for bigger installations, it's also quite common to have a pressure-proof design of the machines, so that you do not actually prevent the risk of explosion, but the equipment is, let's say, robust enough to survive the explosion.
Okay, thank you. We have another question. Production scrapes aren't always on a roll or cut into short length. How do you deal with larger bales or very long length? Feeding and also energy capacity them isn't exactly straightforward.
Mhm. So these cutting mills, so this is the cutting mill at the test center. That's a rather small one. We have much larger ones, of course. For this kind of throughput, a smaller mill would be sufficient. But of course, you need to handle the volume as well. And so, as you can see in this design example here, you can use a larger cutting mill in order to be able to handle these voluminous fragments or bales as you want. And from what we've seen now, the scraps are collected usually in barrels. So let's say, maximum size of the barrel would be the maximum size also of a let's say feed fragment or feed particle, if you would like. Yeah, there are measures in this feed area of the cutting mills that can be used. So we have a lot of experience in in-house recycling for film production, and there you have the same problems that you have all kinds of forms of these scraps or residues that come into the process, and there's let's say some measures that can be taken for compressing the material before feeding into the cutting mill and so on.
Okay, so we have two further questions. Now it's 2:30, but I think we can take these two questions. Do you have experience in compaction or briquetting process with the fines produced at each step of the process? Maybe with black mass? What do you think?
Well, so we always we do not only do the grinding or the size reduction and classification, but we also have equipment for compaction. To be honest, at the moment we did not do any tests in compacting the fine materials to granules or pellets or things like this. That has not been done so far, but this might be an interesting option if the usage of the material is not done directly on site, but if you have a transport to another site for further processing, then this might be a very interesting option. I'm very confident that this should be feasible. As I said, we also make compactors, and this is a common, very common way to reduce dust problems and also to reduce, of course, the transport volume of fine particles or powders.
Okay, then we have a last question about your suggested further processing of the active coating material. What further process steps might be necessary before reintroducing the material into electrode production? What about material degradation, especially talking about the binder particle breakage? Any experience?
Well, this is, of course, one question we also focus on during this R&D project I was talking about. But from what we've seen from work that is also published in BMW, for instance, they've tested different kinds of these direct recycling routes, and you can see as long as you have no big changes in the formulation of the coating, this mechanical process does not lead to real degradation of the coating materials itself. I think this is more severe if you use higher temperatures to somehow affect the binder or even crack the binder before the delamination. Then, of course, you also have detrimental effects on the cathode active material itself, so that there's at least some scientific papers out that indicate that the mechanical process has advantages in this respect. But I think there's still room for improvements and further development, and also further research in terms of the reuse of this material.
Okay, thank you very much. Now we are at the end of our talk for today. So thank you very much for joining us today. And a big thank you to our speakers for their excellent insights. And yes, all upcoming virtual talk dates will be published on our website, and we have one more virtual talk before we see us all again in Nuremberg at the end of September. Our last talk is next week on Tuesday, 7th July, and it's our special for Women for Processing, and it's all about AI and digitalization, and of course the female perspectives for future skills for the process industry. So yes, we invite you to take part, and hopefully we see you all in Nuremberg from 29 September to 1st October. And yes, thank you for being with us today. Have a nice afternoon and good time. Bye-bye. See you.
Bye.
Thank you, Verena. Thank you, everyone. Bye.